Hello everyone. Now as a part of our learning on reservoir simulation, in this tutorial, we will learn about PVT model creation. Okay, PVT model creation, PVT model designer that we will use in our reservoir simulation or reservoir modeling, for example. Okay, and we will do that using T-Navigator or rock flow dynamics here using PVT designer. It's a package, it's a software inside T-Navigator, which is very interesting, very interactive and useful for us to model or to create PVT model or fluid properties model that we can use for reservoir modeling or reservoir simulation. Here we are inside the T-Navigator, and as you can see, we have geology designer, model designer, simulation, and PVT designer, of course, and well designer. Okay, here we will create PVT using PVT designer. Okay, so let's go ahead. First, okay, direct our cursor here in PVT, and we want to create a new project, or if you have an existing project, you can open it. Okay, here we will create a new project. Okay, now after pressing the create new button, I will locate the project that we will create in anywhere in our laptop or computer. And in this place, I want to store my project in desktop. I have created a folder named condensate, so I will enter it. And then I will create a project folder, let's say project, enter, and then I will call it, for example, compositional underscore condensate. And the type of the file is tnaf project.tnaf project. So click save. And now we will enter the PVT designer. Okay. All right. So this is the window for PVT designer inside the T-Navigator. You can see this message box. I will click here to close the messages. Okay, so this is the window. Here we have the tree showing the variant, showing our fluid that we will analyze. And this is the component list. And this is the operation that we will do. And as usual, here we have project, setting, files, help, to save. This one is to create project. This one is workflows, project tree, import file, export to file, open experiments. Okay, so let's go ahead. First, I want to show you the settings. Units manager. In this tutorial, I want to use metric unit, but many times I will use field. Okay, barrel, something like that, Fahrenheit. Okay, but in this example, I want to use metric. Okay, so click apply. All right. Now here you can see we can select the equation of state or EOS, Peng-Robinson, Benelux, Schwafer, Reddick-Wong. In this case, I will select Peng-Robinson. And for viscosity calculation method, LBC, Pedersen, or this one, HZYG. In this case, I want to select the default correlation, LBC. Okay, now we will create or we will add the list of the component. Here you can see add library components. If you open the drop-down menu, you can add library components. You can also provide with your component and reset to library components. First, we will add library components. Yeah, here we have the add library components. Okay, you have C1 methane, C2 ethane, C3 propane, IC4, isobutane, and so on and so forth. Quite comprehensively. Okay, and for the non-hydrocarbon, if we go down, yeah, let's wait for a little while. Okay, you have nitrogen, CO2, H2S, hydrogen, oxygen, and so on and so forth. Okay, in this video, we will select nitrogen and CO2, and then I will press Control on my keyboard. I want to go up, and I want to add C1 through C19. Okay, from methane to nonadecane. Click OK. All right. Okay, so you can see I have nitrogen, CO2, and then C1, C2 down to, okay, it's quite slow because maybe the internet connection is not really good. Okay, down to C19. Okay, now I want to create my component, or you can also call it user component. Okay, or for other discussion or other software, you call it hypothetical component. Okay, which is not usual in the, I mean, it's not the component that you see regularly in the textbook, something like that. It's usually for heavy component. So click this one and add user components. Okay, add user components in this case. Okay, you can see add user components here. You can use the custom. You can also generate the component from correlation, and you can select the correlation, for example, in this case, Razy, Dobert, Kessler-Lee, Cafet to Pedersen. Okay, I will use the default setting. Okay, and I will call the new component C20 or C20 plus. Okay, and then let's say I need, in this case, I need to provide data for molecular weight. Okay, in this case, in kilogram per kilomole, and also the specific gravity. Okay, for example, I will use this default number. The molecular weight is 300, and let's say the specific gravity is 0.9. Okay, you can also add component or remove selected components. Okay, so in this case, let's click OK. So now the new component is registered as the 24th component in my list. And you see, you have critical temperature, critical pressure, eccentric factor, molecular weight, critical volume, specific gravity, and boiling point, all of which are generated or obtained from, yeah, library or from the textbook. Okay, these are the numbers that we use all days in our, yeah, chemical computation or experiment. But for the C20 plus, the properties is generated using correlation that I have selected previously. Okay, it's not component that we see in the library. It's my own component. Okay, I measure it, I obtain it, I use it in my laboratory, and then, yeah, I just input the molecular weight and also the specific gravity. And then using that data, the T-Navigator or the PVT designer will estimate the critical temperature, critical pressure, and others for C20 plus. Okay. Now, you see here, I need to provide the data for the composition. Okay. Composition here, or the fraction. And we can provide either molar fraction or in percentage of molar, mass, or percent mass. Okay, here. Okay, so by the way, in this case, I have two samples. Okay, the first one is the lighter one. So I will duplicate first. The first one is, I will call it light. Okay, for example, light condensate. And the second one is the heavier one. I will call it heavy. Okay, so I have two fluids, light and heavy, and they have different compositions. And I have the data, the composition for both fluids. I save them here. I will go to my folder. Okay. Okay. So here I have stored the data for my experiment here, or for my simulation here. For example, the light component. Okay, here you can see the composition, components, and also the fractions, and the heavy one. Okay. Okay. So now I will input the composition into this one. Okay. You can copy from your spreadsheet and then paste the composition here, but make sure that the you have, for example, nitrogen number one, and then CO2, and then C1, and so on and so forth. Okay. You need to be careful with that. Okay, which one comes after, which one is before, something like that. Okay, so I will prepare my data, I will copy my data and paste the data here. Okay. Okay, so I have copied my data and I will try to paste it here. Okay. All right, so now you can see I have pasted my data here. So I have provided with molar fraction. Okay, molar fraction, not the percentage of it, for the light component or for the light fluid. And I will go to the second fluid, which is the heavy one. Okay, I will input the molar fraction. So I will copy my data and paste it here. Okay, I have copied my data and I will try to paste it here. Okay, so far so good. And please make sure that if you sum all the components, sum the composition, you will get 100%, or you will get 1. If you use fraction, then the total of it will be 1. If you have percentage, then the total of it will be 100%. In this case, I achieve 1 kilogram mole per kilogram mole for fraction. So it means that my composition is already correct, from nitrogen down to C20 plus for the light component and also for the heavy component. Okay, so far so good. I will minimize this column. Okay, so what next? After providing the composition, now the next step is I want to create saturation pressure curve. Okay, saturation pressure curve. Now we start to be more serious here. Click plus. Okay, experiment, and then select saturation pressure. Okay, saturation pressure is really, really important. Okay, I will call it saturation pressure. Okay, and then here we need to provide the number of stages and also minimum and maximum values. And we can also check the calculate critical temperature. So I want to create, or I want to calculate the critical temperature. And for example, I just want to have 10 stages starting from 20 degrees Celsius, 20 centigrade to 200 centigrade. Okay, so You can also allow different options for different variants. If you have different variants, click OK. All right, so now this is the saturation pressure. Okay, for the this one bubble point pressure and also the dew point pressure. You see, this one is bubble point and this one is the dew point. Okay, if you tick, then you will not see the bubble point pressure, and if you untick the dew point pressure, then you will not see the dew point curve. Okay, and also you can see the picture and you can see the table of it. Okay, temperature, variant for the light, and yeah, just see this one for the light. If you want to know the light component, of course, and the heavy one, if you want, and both of them. Okay, so this is very important. The saturation pressure, the bubble point pressure, and also the dew point pressure are really important. Okay, so now we can generate after providing the composition. Now we as engineer or as analysts can estimate or maybe roughly the saturation pressure. We can know the bubble point pressure and also the dew point pressure. Okay, and the next one is we want to create the phase envelope. Okay, open the phase envelope setting. I will call it phase envelope. Okay, here we need to specify the initial temperature, the temperature and pressure step. And we can also check the hydrate formation box here if you want to see the hydrate curve. Okay, so that the hydrate curve will appear in the phase envelope. All right, for this case, I want to start from 20 degrees centigrade, and I just want to maintain the temperature step being 1 degree centigrade, and for the pressure, 1 bar. Okay, again, we can select hydrate or not. In this case, I just want to focus on the phase envelope itself. So yeah, I will not tick the hydrate. Click OK. Let's wait. All right, so this is our phase envelope. Interesting. You can know the critical temperature, critical point pressure, condensate bar, condensate term, and critical temperature coefficient from here. Okay, you can also get in the table if you want. Okay, and yeah, you can also adjust, for example, the property of the picture. Okay, you can do that. Okay, for example, if you click this one, right, show or hide graph options, something like this. This one, you can see the yellow color. You can click and change. For example, I want to select red one. Okay, select red. Okay, you can see, but I just want to go back to yellow to make it clearer. And then you can change the size by changing the scroll, something like this. You can show or not to show the filling. You can do that. You can be creative. Okay. And also maybe not this one. Continuous. Okay, what else we can have here? Dotted or continuous, show filling. All right. And here again, the table. Okay, this is for the custom. Okay. All right, so far so good. So from here, okay, I want to add sample. Okay, sample is really important. Here, click samples. Now you can see for sample, you can provide CCE, constant composition expansion, and CVD, constant volume depletion, and also, for example, sample for relaxation, sample for saturation pressure, separator test, swelling test. In this case, I want to do CCE and CVD, which are quite normal when you construct a PVT model. Okay, so first one, you click this one, CCE, or I want to create CCE, open the drop-down menu, select CCE. And now you will have CCE sample 1. You can also rename if you want, or call it CCE sample. Okay, again, in CCE sample, you can have many experiments, many measurements, molar fraction of oil, oil formation volume factor, gas formation volume factor, and so on and so forth. It's quite comprehensive. You can do many things in CCE experiment. But in this example, in this tutorial, I have data for relative volume. Okay, so we go to relative volume. Here we will have table, pressure, and the relative volume. Okay, so I will go to my data. Here you can also check this one. I have the data here for CCE, pressure versus relative volume. Okay, this is the data. Let me check. Let me try if I copy from the text document and then paste it here. Can I do that? Or I can do that. It's interesting. Okay, so this is my data, the pressure in bars, bars absolute, Barca. It's not Barcelona, of course, and relative volume. So you can see this is the table and this is the plot, dimensionless quantity, relative volume. Okay, so far so good. And the next one, I want to upload the data from CVD. Okay, CVD sample. I want to rename the CVD with CVD sample. From CVD, I have data for gas Z factor. Okay, gas deviation factor. And I will go to my data, CVD pressure versus Z factor. I will copy my data from my text document and then paste it here. Okay, so this is the plot. Again, Z factor is dimensionless. So dimensionless quantity, which is gas Z factor, plotted against pressure in Barca. Again, it's not Barcelona. Okay, so we will go to, from samples, we go to compositional variance. Here, previously, we are in samples down there. Now, because we have provided T-Navigator with experimental data, now we also want to do experiment in our operation. So click plus, experiments. I want to do CCE first, CCE. All right. Now we will call it CCE. Okay. We have two options actually, draw from range data or draw from sample here, from range or from sample. Of course, we have provided T-Navigator with sample, so I will take from sample. And the sample is CCE sample. Okay, I can go directly to OK, but let's check. Standard condition pressure, this one in bars, and standard condition temperature, 15 degrees Celsius. Okay, gas formation volume factor, we can use the default selection. So click OK. So let's see. It's not molar fraction or this one, I will uncheck. So from CCE, I will take this one first, CCE. I have the data for relative volume. Take this one. Okay. So you can see I have the plot, and I also, for example, I have the data Now I'm showing you this one, the heavy relative volume, this dark blue line, and the relative volume from data, which are the dots. The line is taken from the correlation, okay, the correlation to construct the relative volume, whereas the dots are the data. I can show both the light and the heavy component. So you can see the purple now is the heavy, and then the dark blue is the light component. Okay, so more or less quite match for the relative volume. Okay, and the next one, I want to check the CVD, experiment CVD. Okay, for the CVD, I will call it CVD. And again, I can use the range or from sample. Here, I will take the sample. Okay, and then again, standard condition pressure and then standard condition temperature. Click OK. From CVD, I will take this one. I have data for gas factor. Now you can see they don't match actually. For the data are these dots, but the light component only, if we construct the gas Z factor, we will have the brown color, the chocolate one, whereas from the heavy component only, using correlation, we will have for the gas Z factor, the purple color, the purple line. So they don't actually match, but that's okay. So from here, we will go back to the components, and now we will create matching. Why do we need to do matching? Because at the end of the day, what we will use in our reservoir simulation, it's not the data, but the correlation results. Okay, the correlation, or we can also call it the model, the PVT model. So we will not use PVT data in our reservoir simulation, not PVT data, because PVT data is very limited. We only have several dots or several data, but what we will use is the PVT model. Okay, so what we will use is PVT model, and PVT model is constructed using correlation, and the correlation need to be matched with the real data. Okay, so that's why we will do matching. So to match the PVT with the samples, okay, to match the PVT model with the sample or with the data, we need to specify the components that we will use in the matching, and we will match the CCE and CVD experiments, and we can also add new match variant. Okay, so now what I want to match is actually, of course, the most uncertain component, which is C20 plus. For this one, for N2 CO2, the critical temperature, the critical pressure, the eccentric factor, all of them, I'm 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 certain with all of the numbers there, because they are, yeah, they are from library, they are from textbook. Okay, but C20 plus is not from the real data from textbook, it's from estimation using correlation. So the C20 plus, I need to match the C20 plus. Okay, so C20 plus, I need to match. The first one is for the light. So highlight the light component, and then highlight the C20 plus, right click, and you can see this one, matching, use for matching, which means I will use C20 plus and I want to do matching with C20 plus. Okay, so yeah, now C20 plus will be used for matching. And not only that, I will also do I will also include this one, C1, C2, and C3 from Peng-Robinson equation of state. I will use that also for matching. This is very important. Use for matching. Okay, so again from here you can use the operation that we can do here. We can select matching samples to construct or to do the matching. We will press matching. Okay, this one. Okay, so let's be careful here. Okay, we can leave the others as per default, but what important is this one. Okay, I will leave this one here. Experiments that we will use for matching. Okay, so in this case, I want to use light using CCE experiment. The sample will be CCE sample. And then I will click add. The second one is the heavy one. And I want to use CVD for the experiments. And sample will be CVD sample. Okay, and then we have weight here. I will use weight 1 for light oil, for the light. And for the heavy one, I will use weight of 3. Because this experiment displays greater discrepancies, the heavy one. You see, when we want to match the Z factor, okay, when we plot the Z factor, they don't match. So heavy, the CVD show higher discrepancy. So I want to put more weight on this heavy one. Okay, and then here for the variable options, you can check again. You can put some limit, minimum, best value, and also the maximum. Okay, so for the C20, okay, I want to put some limit so that it will not switch with C19. I want to change the critical temperature, the minimum, to be 780. So it will not switch with switch the order with C19. So I will put limit, minimum should be 780, so that it will still be higher than C19. Okay. So from here, others are okay. Click run matching. Matching progress. Okay, let's wait. All right. Previously matching options, now we can quality control. From CCE, we have relative volume data, and now you can see the matching before and after. And you can see the after one is not really good, but yeah, maybe we can use this one. Okay. And what about, or we can also do run matching again. And what about Z factor? Okay, for gas Z factor, you have dots and you have the before, which don't match, and after, which are quite match, but not really match, I think. Okay, but we can use this one. Okay, but maybe you want to do another matching, for example, run matching again if you want. Yeah, let's wait. Yeah, again, the weight is really important. If you put more weight on heavy, then the matching will try to put at greater effort to match for the heavy one with the more weight. So if I change the weight to be 1 and 1, the run matching result will be different. And let's see. Okay, now you can see the after one is actually better than before because now I use more weight, one on CCE and one also for CVD. So this is the matching for the light, and then this is the matching for the heavy. Let's say I'm quite satisfied with that. So we can use the matching result, add match variant, click this one. And now we can call it matching variant. Click OK. All right, and close. Okay. Okay, now I have matching variant for the light one and matching variant for the heavy one. Okay, which are very good. So now let's say this one is data, light one and heavy, the data, but we will not use exactly the data on the simulation, on the reservoir simulation. What we will use is the model, and the model needs to be matched with the data. And the model, the first model that we have is the matching variant. Okay, so we will not end here. We will continue with lumping operation. Okay, so from here we will go to lumping. Okay, but again, we can check the quality of the matching. By the way, you can, yeah, neglect this one. Some interruption, small interruption there. Saturation pressure. If we untick this one, and then for the light, and then for the heavy one, again, the phase envelope for the light and for the heavy, of course, and then the CCE. Okay, the light and the heavy one. Okay, and then also for the CVD. Again, sorry for this one. Okay, now let's see, this one is from the heavy component. Now quite match, but not that match, but we can accept that. And also for the light, the chocolate or the brown color, which is quite acceptable. Okay, so from CCE and from the CVD, we can see that it's quite match. Okay, the matching variant, the model that has been matched, I think it's quite acceptable that we can use this one for our reservoir simulation. Okay. All right. So far, so good. And let's say if we go back to the component, okay, we can, and then highlight the light component. Let's say, what do we have here? We can, here you can see show changes after matching. Okay, we can take this one, but this one, show changes after matching. Okay, here you have show changes after matching. Now it has been highlighted. Okay. Again, for the C20, and then for the C1, C2, C3 in the Peng Robinson. So if I untick this one, you cannot see the highlight, But now, after I tick this one, now you can see the changes that have been matched so that the model can be matched. Okay, for the light and also for the heavy, of course. Okay, all right, now, as I said before, I want to do lumping. Okay, lumping is adding many components to form a new heavier component, so that what we have, the new component, which is actually heavier component, we can use this one. You can use that new sample to reduce simulation time. Again, lumping is adding many components to form a new heavier component to reduce simulation time. Okay, because here you see in my fluid here I have 24 components. Compositional modeling, 24 components. If I input all these 24 components in my reservoir simulation, the reservoir simulation will be too heavy, right? The simulation, the model needs to calculate 24 components, the flow rate, the molar flow rate, the mass flow rate for each component, and it will make the calculation time for my simulation very, very long. So I need to reduce the number of the components by doing lumping. Okay, so create, I will gather, I will add many components to form of a single new heavier component. Okay, and we can have two options in the navigator. The first one is using normal procedure, and the second one is to use auto lumping. And I will show you both of the methods. Okay, then again, we will match the new lumped variant. We will add lump variant and we will check the quality control. Okay, so the first one is we will do manual lumping. Okay, we are in the components, the component properties. Now, the first operation is matching. The second operation is lumping. Okay, again, we will do lumping. We will add many components to form a new heavier component. We click this one. Okay, lumping window here we have. In this window, I have all my components from nitrogen down to C20. Okay, let's say I want to lump from C12 to C20 plus. Okay, I will highlight from C20 plus down to from C12, I mean, down to C20 plus. Okay, and here, this one is auto lumping. I go to this one, group components. I want to lump, I want to group, I want to combine from C12 down to C20 plus to create one new component. Click this one. You see, now I have a new group, a new heavier component. And I will rename this one to be C12 plus. Okay, you can rename it as you wish. Okay, here. You can right click and ungroup components, of course. So now I only have, you can count, I only have not 24 components, but I only have nitrogen down to C12 plus. Okay, it's my new model, my new fluid, which I call lump fluid, for example. Okay, and of course we need to match this new fluid, the lump fluid, with the data. Okay, we will do matching again. And we can do that using this one, matching. Okay, of course, we will try to match the model with the data. Okay, here I want to match for the control components. I want to match the molar fraction. I want to match the oil viscosity. I want to match the oil density, critical point. molar fraction of gas, gas viscosity, and gas density. Okay, I want to match all these parameters because they are very, very important for me. Okay, and yeah, I will do the matching. You can use differential evolution, simplex method, particle swarm optimization, which I will use now. Maximum iterations 10,000. You can stop on slow improvement. Yeah. So if the matching showed slow improvement, then you can stop the iteration to make the iteration faster. Number of iteration 1,000, improvement value 2%. So if there is no improvement greater than 2%, I can stop the iteration and I can use the current iteration as my matching. Okay, so sounds good. Points from, yeah, number of stage 20, minimum and maximum pressure 10 bars to 100 bars, the temperature 100. Okay, so let's go run matching. Yeah, again, we want to create new lump variant that has to be matched. So let's go to see the quality control. Okay. This one, molar fraction should be exactly the same before and after. Molar fraction also the same. So how can I tell they are the same? Because you cannot see the brown line. So it means they overlay exactly at the same place. Okay, but you can see if I maximize. Okay, for the density, they are quite match, but not that match actually. Okay, it will be based on your computer, of course. Okay, based on your current matching, which will be different from one computer to other computer. Okay, so this is the current quality control that I have. I can accept it, or I can also I can rerun the matching. Okay, fingerprint plot. Okay, so the fingerprint plot show the molar fraction versus the molecular weight. So it's okay. Grading test, not now. So again, you can decide whether you want to do rematching or you can accept it. For example, we want to do rematching. Okay, quality control. Can I do that? Close first. Okay. What do we have? The message here. The message here. Error in calculating grading test. Yes, of course. Again, we can go back to this one, lumping, matching. Let's say stop on show slow improvement. Improvement, let's say 1%. Okay, run matching. Okay. Okay, now I think it's better. Yeah, okay. So you know what I mean. So we must try to achieve matching. So I think, yeah, we can accept this matching. I can go back to this one, to the components, and you can use this one, click this one, add variant. I will move it a little bit, add variant. Now I want to use this lumping variant. Okay, I want to accept the matching. I'm quite satisfied with that. And I want to call it, because I do lumping for the light oil, I will call it lumping matching variant for light. Click OK. OK. Okay, so now I have lumping matching variant for the light condensate. Okay, and I will rename it as light. Okay, So yeah, I will conclude later. Now I go to heavy, the match one, the heavy one, and I will do the same operation. I want to do matching, lumping, sorry. Okay, so for this one, I will not do manual lumping, but I will use this operation, which is very good, auto lumping. This one, auto lumping setting. You can lumping light components, number of light pseudo components that you want to include, and also lumping heavy components, number of heavy pseudo components. First heavy component, okay, first heavy component that will be the first component of the group, and the k values method. You can use Flash, negative Flash, or Wilson. I will use Wilson. And now I don't want to lump light, but I want to lump the heavy one. And I just want to create one heavy pseudo component. Again, it's a pseudo component because it's not component. It's pseudo because it's unreal. Okay, because it's a group of components. So we can call it pseudo component. I just want to create one pseudo component, which is a group of components. And I want to start the group from C12. So of course, it will be C12, C13, down to C20 plus. Okay, start from C12 with only one pseudo component. So if you click OK, open this one, of course, you will have auto lump from C12. Only one pseudo component, which I will call C12 plus again. Okay, so now I have this one. Okay, so with C12. And of course, I want to do matching. Control parameters all. I will maintain this one, or I want to improve 1%. And the same for this one, the default, run matching. Okay, let's check the quality control. Okay, let's accept this one. I think it's quite okay. Okay, quite acceptable, the matching. I'm quite happy with it. Quality control and also the fingerprint, quite match. Okay, before and after. Yeah, fingerprint plot. So again, we can go to the component, and this one I want to call it lumping matching variant for the heavy liquid or heavy condensate. Click OK. I will close. Now I will call it light, and I will call it heavy. Okay. I tried to rename, but can I? L. Again, if I try to light, cannot. Yeah. Light lamp. Maybe I cannot exactly copy the name, the same name. I just call it heavy lamp or lamp. I think it's better. Okay. So let's make a story. This one is data. The variant one, light data, heavy data from laboratory. Then I want to create a model. The model should be matched with the data. Okay, but with the exact numbers of components which are 24. And the match model is I call matching variant, light and heavy. But if I use the matching variant, the simulation will be too heavy because I have 24 components from each of the light and the heavy one. So I need to do lumping. Okay, I need to group several components to make a new pseudo component to reduce the number of components so that if I use that in my reservoir simulation, the simulation can be more relaxed. The calculation will not be too long. The simulation will not be too heavy, okay? Because now I reduce the number of the components. So I have variant, or you can also call it maybe laboratory, something like that, or maybe a variant. And you can call this one laboratory light, heavy light, matching heavy, lumping light, lumping oil, lumping heavy. You can name it as you wish. Okay, so far so good. Now after lumping, I can blend. Now I can blend the fluids that I want to blend to 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 create just one new fluid. Okay, so blending, you can blend two variants of two wells, for example, different composition, and you will get a new variant with new composition. Okay, so basically you can combine two fluids to create one new fluid. Okay, here you will add two samples, and again you need to match the samples and you can construct new variant. How can we do that? We can do that using this one, compositional blend. So this one, splitting, if you want to split, blend, and fluid recombination, decontaminate. There are several interesting operation, but now I will use this one, compositional blend. Okay, now it's interesting. Now for the variant, I have this one. I will move this window a little bit. Can I? Yeah, this one as the default. Lumping matching variant heavy. Okay, which is, yeah, I want to blend the variant from the lumping group. Okay, and this one is heavy. The fraction 1. Okay, and this is the component. Okay, from the lumping. You see, from the lumping, we only have 16 components from nitrogen down to C12 plus. You don't see C13, C20 plus because it's lumping component. Okay, now I want to add with also lumping, but lumping matching variant light, composition light lumped, and the fraction is 1. Now basically you blend them. Okay, now you will get new composition which are different from this one. Okay, you can, again, let's check. I will remove. So now I only have heavy, and you see the nitrogen 0.022, the composition. But if I add, the composition will change. I will add with the light, yeah. And this is the new composition. The number of components the same, 16, from nitrogen down to C12 plus. Okay, and what's next? Of course, we want to do matching. And the most uncertain component is, of course, C12. Okay, so I want to do matching on the C12. Okay, just as before. So I will click matching, right click matching, and use for matching. Okay, I will include that for the matching. Okay, now I'm quite satisfied with that. I will click this one, matching. Okay, so let's expand the window. Okay, again, I want to do matching with particle swarm optimization, 10,000 maximum iteration. Okay, and then I will stop number of iteration 1,000. Now I go very detailed. Improvement value is 0.001%. So I'm being very strict. Control parameters the same. Okay, and then number of values, yeah, 20. Minimum I can use 50, for example, or you can also use the same 20 to 50, for example, and then let's say the reservoir temperature 100 or 150. In this case, I'm going to use 100. Okay. And then let's check the blend objects. Yeah, of course, the heavy lump and the light lump. And then the variable options, the critical temperature, critical pressure, eccentric factor, yeah, all of them will be included. You can include them when you do the matching. But in this case, I will concentrate on the critical temperature and also the molecular weight. Okay, so far so good. I can run matching. Okay, very fast. Okay, you can check the quality control. Now let's see. Let's check the molar fraction of oil. Okay, molar fraction of gas, oil viscosity, gas viscosity. Now you see this is very important. This is the resulting results. Okay, this is the results after we blend the new fluids, the lumping fluids, heavy and light, into just one component. Okay, so the properties are shown here. Oil density, gas density, and this one from the heavy one. Okay, so far so good. We go to components, and let's say we are quite satisfied with that. Click this one, create variant, and we can call it blend. Okay, so click OK. Now you see you have a new group in the tree, blend, composition 1, and also if I expand a little bit, lumping, matching variant heavy lumped, and lumping, matching variant light lumped. And the main thing is here, composition, which I will call blend. Okay. Yeah, so far so good. Now, based on the tree, you can see I have the data, laboratory data, the match light and heavy fluid, and then I construct the lumping fluid from the matching, and then I blend from the lumping fluids to create one new component. Okay, sounds really great. And now let's say we can call it a day. We are quite satisfied with what we have achieved from now for now, and we can export what we have constructed here so that the results can be used in the simulation. But first, to make it safe, I will save. Okay, I will save the project. Okay, click project and then, yeah, so it's being saved automatically, I think, or you can also save as. Okay, so the next thing that we will do is export. We have several types of files that we can obtain from by exporting. So we will try 4 methods to export all the operation that we have done uh, now. Okay. Okay, so now we will export. We have several methods to export. The first one is export properties, and the second one is export comp vd and temp vd. You will know it better later. And then export as black oil variant or export using regions. Okay, you will know that after I show you. Okay, now from here we can, for example, this one, export to file. Okay, let's check this one first. Okay, so again, I will show you so that you can know it better. This one, export to file. Now you see props blend here in this case. Okay, yeah, again, I have blended the the fluids. Okay, the story is like this. I have data, laboratory data, and I create model that has been matched with the data, and then the model or the matching model, the match model is too heavy, so I just do lumping to reduce simulation time. But after blending, after lumping, I blend the fluid to construct only one blend component. So now I import the properties here, props blend, the name of the file, and the file type is .inc or include. So click save. Okay. Let's wait for a while. Okay, it has been saved. So I go to my folder, go to the project. Now you see I have the TINAF project and props blend, the properties file. Let's go inside, double click. Okay, now you see all these keywords and these component names from nitrogen down to C12 plus. This is the water component names, critical pressure, critical temperature, critical molar volume for viscosity correlation, critical molar volume for each component, and then this one, molecular weight, binary interaction coefficients, eccentric factor, all right, boiling points, all right, omega A, omega B, component paracores, volume shift parameters, and then this coefficient, equation of state, Peng-Robinson, the reservoir temperature 100. Okay, so that's the first method to export. So later on, we can use this file to be included in our reservoir simulation. Okay, so that's the first method. Now we will try the second method. Okay, I will click this one and then go to grading test. Okay, we need to do grading test first. Okay, let's wait. Okay. Okay, so this is our grading test. Okay. Here we need to be very careful. We need to know some important parameters, like for example, this one, the depth. Okay. The depth in our reservoir. So let's say for this case, the minimum depth the is at 2000 meters and the maximum is at 2100, and we need to know the temperature. At 2000 meters, the temperature, let's say, is 100, and the maximum, let's say, 104. And we need to provide the temperature at certain depth, let's say, or the pressure, I mean, let's say at 2000 feet or 2000 meters, the pressure is 600 bars. And we need to generate also this RS and RV. And let's say for the standard condition for the pressure, we can use this one, standard condition for temperature, 15 degrees Fahrenheit. Number of values I can maintain 11. So I will click OK. Now I have the grading test. Okay. What I want is actually this one, the pressure. Okay. You can see the plot and also the table and the saturation pressure. Okay. And also the oil density and the gas density, RS and RV. All right. Very important. This RS and RV will be used in our simulation. And they are plotted against the depth. So let's say for the RS, so that we can read this one or the RV. Okay. Okay, so for the RV, for example, so this one, the green one, I think, is the RV from the blend. Okay. And then this one, the blue, the dark blue, RV. Okay. For the light component, the matching variant. Okay. And also this one, the purple heavy, RV. And yeah, that's if you generate from the matching variant. Let's say I want to focus on the blend. Okay. So actually, for this grading test, I need to do that for the blend component. So yeah, this is very difficult because this blocking me out. So let's say, can I move that? Something like this. Be smart, right? So now I can delete this grading test. I want to do the grading test for the blend. Okay, so let's do the grading for the blend fluid. Do grading test. Sorry, it's quite slow. It's not from the T Navigator, it's from my connection. So I call it grading test. And then the minimum at 2000, it is 2100. And then minimum temperature 100, 104. Input at 2000 meters. The pressure is 600 bars. Absolute. Calculate RCRF, RV. Click OK. Okay. And then tick everything. Okay. All right. So far, so good. Okay. So you can see the plot and you can see the the table, the pressure. So if you see, okay, pressure versus depth, temperature versus depth, saturation pressure versus depth. So these are called grading tests. Okay, and oil density, no. This one is for the gas density. Okay. And then RS, RV, relative volume. Okay. Okay. All right. So far, so good. Yeah, maybe we can also check for the oil density and RV. And here we can export. Now you see, export comp VD. VD is actually versus depth. Okay. Temp, temperature versus depth. Comp, comp. I think comp is component or composition. I think it's component versus depth. Okay, so let's export. Now you see comp VD and temp VD of the blend fluid include files. Okay, .inc. So let's click save and yep, and let's visit the folder. Okay, let's go to the project. Now comp VD and temp VD, and this is the file. Okay, so far so good. Okay, I can close and then I will minimize this one. And then the third method, okay, the third method is also very interesting. I want to create black oil. So I will click this one. Now I will go to PVT to construct black oil. Okay, I will call the tab name PVT. And let's say for the range 20, minimum yes, maximum yes, and not from sample. This one, standard condition, pressure and temperature, all good. Click OK. Now it's quite simple. Now I construct PVT or black oil model from my blend component. So you see for the oil, I have RS, I have formation volume factor, and I have viscosity for the gas, pressure, formation volume factor, viscosity, plotted against RV, and also the water properties. I have water properties. Okay, so good. So if you construct reservoir modeling, reservoir simulation using black oil model, so you can use this PVT as your fluid model or as your PVT model. And for this one, the export is easily can be done here. Export to file. Okay, now you see PVT underscore blend. So that's the third method. Click save. Okay, now I will click refresh. PVT blend opened. Now you have PVT for oil, PVTO, quite comprehensive. And then, yeah, you can go down, PVT props, PVTW, PVT for the gas. Okay. Density, okay, for oil, water, and gas. So click close. Now I want to construct I want to do the last method to export, and I can do that by using this one, export to file, compositional variant, or can also black oil variant. Okay, so for example, compositional variant, this one, you can see the units metric. I can have several regions. Okay, EOS region. I can have, for example, the first region, I will use variant, and variant common data valid. And this one, for example, I can open and I will use, yeah, variant. For example, for the first region, and then I will add region. For example, I have two regions in my reservoir with different PVT, with different PVT model. Okay, can be like that. And for the first region, I will use variant. I can use the data, right? The data. But for the second region, I cannot use data. For example, I don't have exact data, but I can use model. For example, I can use matching variant. Okay, matching variant. So the first region will use variant, and the variant is the data, laboratory data. And the second region, I can use the matching variant, for example. This is just for example. Variant SC, yes, variant. And then you can expand the composition. For example, this is for light oil or light component. This is for heavy component. And you can also include all properties listed here. You can select default, or you can select all. You can deselect all. Usually we can use select default. So we can only include several properties that are common to be used in reservoir simulation. Okay, so from here we can easily export by clicking this export button, and the name props, save, and check the folder, and you will have props file you can open, and you can have this one. Okay, comp, number of components, 24 here. Okay, from nitrogen down to C20 plus, the name, water component names, water, critical pressure, critical temperature, and also, yes, critical temperature EOS, critical molar volume, and so on and so forth. Okay, so really interesting, right? So we can call it a day. I just want to give the summary. So in this example, in this tutorial, we have created PVT model using T-Navigator or PVT Designer in T-Navigator. We have data. We have data from two components, the light condensate and heavy condensate. We have CCE experimental data. We have CVD experimental data. And then we want to create the model. And we have created the model, and the model needs to be matched. And after matching, we have this matching variant with 24 components from nitrogen down to C20 plus for each of the fluid, light and heavy. And because they have 24 components, they if they are included in the reservoir simulation, the calculation will be very long because of the numbers of the component, 24. So I do lumping to reduce the number of components. From 24, I reduce down to, if I check, down to 16, I guess, if I'm not mistaken. Yes, 16 component. I lump from C12 to C20 plus, I create a new pseudo component, which I call C12 plus. And after lumping, of course, I do matching so that I get a good match lumped component, which I call light lumped and heavy lumped. Okay, but now I combine the light and the heavy light, the light lumped and the heavy lumped to create one blend fluid. Here, one blend fluid. And again, I do matching for the blend. So I get the final model, final PVT model, which I call blend, which has been matched. So now I can use this blend PVT. I can use this model in my simulation, reservoir simulation. And so that, and in order for me to be able to use this blend fluid, I need to export. And I have several methods. I have 4 methods to export. I can do export by properties. I can do export by comp-vd and temp-vd. I can do also PVT, black oil, and by regions. So I have exported the result here, the model here with 4 methods. All right, so it's quite long tutorial, but I hope you get a clear picture about how PVT modeling is really like. Okay, so that's all. I hope you enjoyed the video. I hope this video is useful. Thank you so much for watching and see you again in our learning of reservoir simulation. Okay, thank you.